Okay, welcome back. Thanks for staying until the last last day, survivors of this ordeal. Today I want to say a little bit about the construction of polar codes, because what we saw was that once you decide on which channels are good and which channels are bad, then you have simple encoding and decoding structures. These things are going to take n log n time to encode and n log n time to decode a block length n polar code. Decoding is, of course, not the maximum likely decoding that we're talking about, but this successive decision of the symbols, which is in general suboptimal. But as we saw yesterday in the last part, this is sufficient to achieve all rates up to the mutual information of the underlying channel with as small error probability, a small block error probability as you desire. And indeed what we saw was that the block error probability goes down like 2 to the minus the square root, exponentially smaller than the square root of the block length. And this estimate of the 2 to the minus square root of block length is not too bad, because even if you don't use the union bound on the probability of the block error, if you just simply take a look at any one of these symbols, u being decoded incorrectly, it's going to give about a z parameter of the underlying channel that you're sending. And what we saw also last night from the argument about how does the z behaves, z cannot go down faster than this exponentially small than the square root of block length. So to the first order of approximation, the polar codes do have this 2 to the minus root n behavior of the block error probability. Okay. Let me just maybe remind you as to how things were. For the BEC, so polar codes. So one can, of course, give a cheating answer to this, saying that, well, the construction you do only once. Okay, so you construct the code once, and then use the code many times over to transmit data. So whatever you do once, you do it offline. It's a process in which you go home and you think very hard to do this construction, and then you're done. So in a sense, the construction complexity does not really matter in terms of the implementation of polar codes. However, if the construction is very difficult, then even doing it once might be not feasible. So some things, I mean, you cannot do them even one time. Okay? So forget about doing it many times, but even once might be a difficult proposition to take on. So consequently, it's important to understand how difficult is it to construct polar codes. If it ends up being, let's say, doubly exponential in the block length or something, then okay, you're in trouble. Okay. Because if the block length is a billion, exponent 2 to the million, if it'll take you that many computations, I mean, nobody's ever going to do this. And if you see, for the case of the BEC, things were simple. So for the BEC, because we could explicitly compute in essentially n operations, or maybe n log n operations, whatever, what are the erasure probabilities of the synthetic channels that you created. I mean, you start with p, you compute p squared 2p minus p squared. You then compute these things. Okay, so there are, if you have here at level I, you have here n is equal to 2 to the I numbers. And the total number of operations that you do in this tree is the same as the total number of nodes in this tree, which is 2n, okay? Because you have n plus half n plus quarter n, etc., all the way to 1. You're summing a geometric series. 2p minus p squared. Sorry, I wrote terribly. So in essentially 2n multiplications, what you have is all the erasure all the channels here, so you can decide which one of these things are good, which one of these things are bad. You also know that among these 2 to the I numbers, about a p fraction is going to be bad, and 1 minus p fraction are going to be good. That's what we know. So you can identify which ones they are easily. So for the BEC, no problem. Okay. But for another channel, what you had to deal with is the following thing. We had to worry about the parameters of the synthetic channels which are here. Okay? Either you compute a mutual information, or you compute a Bhattacharya parameter of these channels. Okay? But if you take a look at what is the what are the outputs? What do these channels look like? So at the level I, a channel WS, which is in here. Okay. This channel WS, suppose it is SI, it's a channel which maps one of these U's, U something, okay, some index here, whatever it is, one of these U1 up to U2 to the I, one of these U indices, into the output, which is Y1. But how many Y's are there? There are 2 to the I Y's, because these synthetic channels are created by using the underlying channel 2 to the I times. Okay. And then you have here also the previous U's. Okay. So whatever this index is, you also have the outputs which are there. Okay. Now, so this is the output alphabet, output symbols of your channel. So how many output symbols are there? Okay. Suppose the original Y was, let's say, binary. Okay. Let's say least trivial, the first non-trivial case. If the Y is only unary Y, there's only a single Y, there's no point communicating. The capacity is 0 anyway. Suppose only 2 Ys, that's going to give us the smallest possible output. So it's a very conservative estimate as to this thing. So you have 2 to the power 2 to the I possibilities for these Ys. Okay. And then there are more possibilities coming up from these U's. So the output alphabet size of any one of these channels, so of the output alphabet of W to the S1 to Si, one of the generic channels over here, is at least 2 to the power 2 to the I. Okay. Not so good, right? Because now if you want to compute, for example, the Bhattacharya parameter of such a channel, you have a summation over all outputs of this channel, something. So it'll make at least this many computations to figure out the Bhattacharya parameter of one of the channels here. Okay. And similarly, mutual information computation also requires at least this many operations. Okay. So do this thing in a brute force fashion is going to kill you. You try to do this. Okay. Even if I is equal to some modest number like 10, so a block length of 1,000, this is 2 to the 1,000. Okay. So you don't want to touch such numbers. Okay. 2 to the 1,000 is 10 to the 300, right? That's you don't do this. Okay. So now, then the question is, okay, how do we get around this? So one possibility, I think it was first suggested by Arikan himself, is to do simulations. Okay. So what you do is the following. You run the encoder and decoder without any frozen information, okay, but with the Gini. Okay. So the encoding is done in n log n steps. You put some random U's. Okay. You encode them, find the X's, pass them through the channel. Okay. You get the Y's. You run the Y's through the decoder. It also takes only n log n steps. So each iteration of this simulation as to taking some U's, sending and receiving them, is going to take you about n log n operations. And then see which U's you have decoded correctly, which U's you have decoded incorrectly with the help of the Gini. Okay. Do this thing 1,000,000 times, okay, say, and then you have then 1,000,000 estimates as to, for each channel, you have 1,000,000 estimates as to did I decode correctly or incorrectly in each of these channels. The good channels, you will figure out that, okay, you're decoding always correctly. Okay. And the bad channels, you'll be decoding essentially with probability half wrong. Okay. So you'll quickly distinguish between the good channels and the bad channels. After 1,000,000 runs, you would expect that on the good channels, you make no errors. Okay. And on the bad channels, you make about half errors. Consequently, the chance that a bad index pretending to be a good one at the end of your simulation is very small. Okay. Something which makes errors half the time is supposed to make very few errors over 1,000,000 trials. It's not going to happen. Okay? So you can reliably identify which channels are good and which channels are bad. That's one possibility, and it only takes n log n times your confidence, how many experiments that you want to do to obtain some confidence there. Can be done offline. Okay? If 1,000,000 is not good enough for you, do it 1,000,000,000 times. Okay? You can do this. It won't take you more than a few days. Okay? So if you could design a good code in a few days, okay, why not? You have your design, then you use it for years. Okay? So you put it in a chip, okay, that chip is going to work on your cell phone, whatever, for a long time. So the design time that you spend is amortized over the lifetime of the devices that you built. This is nice, but the following problem appears. If you want to, for example, use these codes, so one advantage of these codes that I've been telling you about is that there is no random element in their design. So you can give precise guarantees on their error probability. They have no error floor and so forth, so maybe you want to use them for applications which require very high reliability. And suppose you want to use these codes for an error probability which is very small, say 10 to the minus 12, 10 to the minus 15. Then your experiments have to be of this size too. At the design time, if you want to identify a channel which is better than, whose error probability is less than 10 to the minus 15, this requires you to make 10 to the 15 experiments at least, so that if you don't see any errors in 10 to the 15 trials, then you can be fairly sure that maybe, or you can be somewhat convinced that maybe a probability was less than 10 to the minus something close to 15. Without making that many experiments, you cannot be sure. Right? If you make only 1,000 experiments, I mean, maybe it is 10 to the minus 4, maybe it is 10 to the minus 6, but I mean, you won't know. And that number of experiments is difficult to make. It might take you now years to make these experiments. Okay? 10 to the 9 was maybe a few days, but if you ask me a million times more than this, it might take me a century to do the experiments. So it's not feasible. So we better find a better way to do this, a different way to do this, which doesn't rely on simulations, but on something better to do what we are doing. Am I clear as to what I'm saying here? Okay. So remember, the difficulty that we had to compute things explicitly was the size of this output alphabet. If I can somehow manage to control that, if I can somehow get a handle on the output alphabet size and ensure it does not grow too fast, I'll be okay. And that's what we will do. Okay? So this idea is due to Alexander Vardy and Ido Tal, who were at that time both at University of California in San Diego. Ido was a postdoc, I think. Alex is still there as a professor. Ido is now in Technion, so he finished his postdoc and went back to Israel. He's still there, doing nice work. And the idea is the following thing. But before telling the idea, I should tell you a few things about channels and degradation. Okay. So it's a very general concept. And also a very simple concept. Suppose you have a channel with input x and the output y, okay, like this. And then suppose I take its output and I process the output by some machine. Okay? So I put here a box. I take this output, I do some operations on it. So I compute maybe a function of y. Okay? So there's this box. It might compute a function, okay? But in general, it might even compute a probabilistic function. This function that you compute may not be deterministic. It might have some additional coin flips and so on and so forth in this computation. So you obtain some output. Let me call it to be z. This is a bad letter because I'm going to use z for the Bhattacharya parameter of the channel. But you won't get confused, will you? This z is simply is an output letter of this box. It is not necessarily the Bhattacharya parameter of this thing. So this could be, for example, a function of y, okay? Or in general, this might have a probabilistic device in it. But the point is the following: this probabilistic device should have no, for example, if you are using as part of your probability the things at the input, that's not legal. Okay? So the meaning of this diagram is that once you tell me the y, the z is independent of x. Okay? So condition on the y, z should no longer have any dependence on the x. Otherwise, it means that this diagram is not faithful to the physical reality. In fact, there are some hidden links between the x and this box, which is not captured by the diagram. Meaning of this diagram is that the x and the z become independent conditioned on y, or in the terminology, fancy term of the probability theorists, x, y, z forms the Markov sequence, the Markov chain. Okay? So, right? So the x and z are independent conditional on y. Okay? That's the meaning of this diagram here. If you have such an object, I mean, in general, what we have is the following. This could then maybe described by a p of the z given y. Okay, so this channel is described by some w of y given x. Okay, so when the x is sent, the y is created from the conditional distribution w of y given x, and when the y is given, z is created from the conditional distribution of z given y. Okay. This might be a deterministic distribution, so that a given y might determine exactly what the z is. Okay. And in the case, you have a function box here. Otherwise, you get the probabilistic box there. Okay. All right. So there's P for processor. Okay. So now there are a few things about this process. What does it do to respond? So if I call now this thing the channel V of z given x. The overall structure is that I send the x and I receive the z. So now let's now see. Let's now try to compare I of xy versus a dilemma. I of xy is always more than I of xz. So processing of the output is never going to help you. Okay. And the proof of this, I'm not sure if you saw this thing in the previous lectures. It's a triviality. Let me just write it down so that, okay, so the proof. You take a look at, so the trick for improving these kinds of stuff is the following. You say, I have a mutual information on x on both sides, but other objects on the other sides. Okay. Let me then write a mutual information with both these objects on the same or the same expression there, and expand this thing by the chain rules. Okay. So this thing, x and yz, is on the one hand equal to I of xy plus I of x and z given y. That's the one way to do the chain rule, starting from the y first. Or I can start from the z first. So this is also equal to I of xz plus I of xy condition on z. Okay? Those are the two possible chain rules I could apply to if you have only two objects on one side. There's only two ways to expand this mutual information. Okay. All right. So now we had said that the x and the z are independent conditioned on y. So this means that this quantity is 0. So this is 0 because conditioned on y, x and the z are independent. Okay, so this is equal to I of xy, and this guy is obviously bigger than I of xz. Because I had two terms here, both of them are non-negative. If I ignore one of them, the other one must be a lower bound, and then we're done. Okay, so I of xy equals this, which is greater than I of xz. Okay, you read this thing, okay, snake it around. So we're done. So, okay, so this processing can never improve mutual information. All right. What about the Bhattacharya parameter? So this was channel W. Okay, there's a Bhattacharya parameter. Now this Z is not the channel output; it's the Bhattacharya parameter of W. And there's a Z of the channel V that we just created by processing the output of W, and then we have a new channel from X to the new output Z. Okay, all right, and this is like that. Okay, so the Bhattacharya parameter of W is better in the sense of being smaller, okay, than the Bhattacharya parameter of V. So we should also prove this one. Okay, this you may not have seen in the previous One was in the lectures, I'm sure, but the second one, probably not. So let's see. Let's take a look at this Z of V. I'm supposed to go over all outputs of the channel V. Okay. I'm supposed to write down the probability that the channel output is equal to Z, condition on X being equal to 0, times the probability that the Z is equal to Z, condition on X being equal to 1. That's the definition of the Bhattacharya parameter of a channel. Right? Okay. Now what is this guy? So this guy is simply, if X is 0, you can get to a particular output Z by first going through some Y, and then from that Y I'm supposed to get to Z. Okay? This is a summation over Y, W of Y given 0, and the P of the Z given Y. Right? Okay. We have that. And we have this guy here. It's exactly in the same form, but maybe not to confuse things, I should use a different dummy summation variable, let's say Y prime. Okay? And this is the W of Y prime given 1, and the probability of Z, the same Z, given Y prime. Okay? Fine. So now, what are we going to do here? Okay. So now, when you have these kinds of things, you should think of the inequality of the following type. If you have a summation over, let's say, AY squares over Y, a summation over Y prime, BY prime squares, this product is what appears in the Cauchy-Schwarz inequality. This is, you're taking multiplying the L2 norms squares of two vectors, the vector A and the vector B. This is bigger than the inner product squared. Actually, this and these Y's are integral over the same alphabet, right? This is this is Y over Y, Y prime over the same object Y. This is bigger than summation over Y over the same thing, AY times BY quantity squared, right? This is Cauchy-Schwarz, or Cauchy-Schwarz, Bunyakovsky, whatever. So there are many people associated with this thing. So this is a T in the Cauchy-Schwarz or not? I always get confused. Anyway, put a T if you like. So the A's that are here are the square roots of these things, right? Okay. I have a square root sign outside, so this is nice because I can do this, okay, and take the square out. Right. So fine, so the square root is already there. So this is bigger than summation over Z. And what did we say? It's a summation over all, the square is bigger than summation over all Y, AY times BY, and A was the square root of this, and B was the square root of that. So I have inside the square root here, the W of Y given 0, P of Z given Y, W of Y given Y, P of the Z given Y. Okay. P of the Z given Y appears twice, so it's a square, but I have a square root, so this one comes out. P of the Z given Y and the square root of W of Y given 0, W of Y given 1. Okay. It's a double sum. I can do it in any order I want, so let me do it in the order of the Y and the Z first. Okay. If I do the Z summation first, okay, this guy here does not depend on the Z. It comes out of the Z summation. Okay, and I'm summing over the conditional probability of Z for a particular Y over all Z. That equals to 1. Okay, this thing equals summation over Y. Okay, because the Z summation over the P of the Z given Y, for a fixed Y, it is equal to 1. And this is what we are left on the right-hand side is nothing but the Bhattacharya parameter of the channel W. Okay. So this degradation, not too surprisingly, it makes the mutual information smaller and the Bhattacharya parameter bigger. Okay, so worse in both cases. Okay, all right. Okay, good. So now, then the idea as to how to. Oh, I should say a few more things. Okay, hold on. The second thing I want to say is that is this. Polarization also commutes for degradation. Okay? So suppose, let me use this following sign. Let me use a sign such as this to denote a degradation. So we'll say that to denote degradation. So W, so V is this funny less than or equal to sign W to mean that V is a degraded version of W. I start from W, I process as output to obtain the channel V, okay, to mean some processor, and this combination is called to be V. Okay, this is the meaning of V. Okay. Good. Okay. Okay. So now here's some obvious statement. Okay, so remark. Destroying chalk kind of thing. If V is worse than W, suppose you take two channels, V and W, one of them is worse than the other, and then suppose you polarize them both. Okay, then take a look at V plus and W plus, and take a look at V minus and W minus. Okay, how would you think that these would be ordered? I guess it's not to stretch my imagination that this degradation will be preserved after polarization 2. If I start my polarization process on a worse channel, the synthetic channels that I create are going to remain worse. Okay? And the proof of this is essentially by diagram. And I have these processors to create the Z1, Z2. So this is a V, and this is another V, right? Okay. So if you look at this diagram, okay, let's say W minus is the channel between U1 and Y1, Y2, whereas V minus is the channel between U1 and Z1, Z2. So clearly, this V minus is the channel W minus whose outputs Y1 and Y2 are processed by the same processor, one for Y1 and one for Y2. So this V minus is realized by processing the output of W minus. So consequently, V minus is degraded with respect to a W minus. Okay. Similarly, W plus is the channel between U2 and Y1, Y2, U1. And as well as the V plus is the channel between U2 and Z1, Z2, U1. Again, the same thing. You take a look at the output of W plus. You process the first component through the same processor that was degrading W to V. You take the second component, you process it with respect to the processor with degrading W to V. Third component, U1, you leave alone. Okay? So clearly, you obtain the output of V plus by processing the output of W plus. Okay? So, I mean, this is too trivial of a statement. To give a proof is maybe more confusing than the statement itself, but okay, the proof is simply the diagram. Okay, all right, good. Okay. So now, idea is to how to estimate the or find the good indices of the after the polar process for W. I'll try to do it, and not to do it with too much complexity, is to use degradation in the intermediate channels that I create. So I'll tell you about this thing a bit more. But now, maybe I should be a bit more careful as to what I say. Then you have a procedure to identify the good channels. And suppose your procedure is approximate. So you say that I'm not going to run the exact computations of the synthetic channels because they are too big of these output alphabets. I'm going to estimate if these channels are good or bad. Your estimation should be only in one direction. You should never claim that a bad channel is good. You should never identify a channel which was actually bad. If you identify as being good, then you might be in very big trouble, because if you now use that channel to send information, you'll be making errors on that, so it'll be bad. You should only make errors in the direction of saying identifying good channels as bad. Okay, that's okay. You lose rates. Okay, you might say that you may not be able to achieve IW anymore, because some of the good channels in the IW fraction of the good channels now you identified as being made bad channels, so you don't use them even though you could. But at least the channels that you're using are still good, so that when you transmit data over them, you're not making mistakes. Okay, so our estimation procedure should be making errors only in the bad to good direction. No, exactly opposite. So you should identify only good channels as being bad. You should never misidentify a bad channel as being good. Okay, right. So, all right. So let's see if we can come up with such a procedure like this. So the idea is as follows. Okay. So we start from some channel W. Okay. And then what I should have done is the following thing. I should have computed this W plus, computed W minus. I should have computed this W plus plus. By computing, I mean that you should find me the statistics, the P of the output of this channel given the input of this channel. That's mean the computation of a channel. W plus minus, W minus plus, W minus minus, and so forth. This is what I should have done. This is what I should have done. Okay. Instead, I'll do the following. I'll say, this channel W plus, its output alphabet has become too large. Okay. I'm going to replace this channel by a degraded version of this channel whose output is smaller. So I'm going to process the output of W plus to merge some of the outputs to the same output. As we had done, for example, we had these channels whose output was, there was A-terry output. And then we said, let me label some of these things as stars, other ones as double stars, other ones as triple stars. The way I had done this labeling was completely lossless, because you can simulate the star channel from this channel by simply merging the outputs of this. And the star channel's outputs, we could generate this one by splitting the outputs without loss of mutual information. Okay. Here, I might lose mutual information. I'm going to simply say that I don't want to deal with channels whose outputs is, let's say, if this was your W plus might have now, I'm not sure how many I wrote here, suppose this is 8. W plus might have 8 squared times 2, because Y1, Y2, and U1, 128. 128 I don't want to deal with. I'm going to reduce the 128 back to, let's say, 10. Okay, so I'm going to take from the W plus channel, suppose this is W plus, I'm going to say that these three outputs I'm going to merge it into a single output star. Okay, these ones I'm going to map it into the output triple star. These ones I'm going to merge into a triple star. So this is the W plus, and this is this processing P, which computes the output Z from this Y by simply identifying a whole bunch of different Y's as a single Z. Okay? So you merge things back. By doing this, I might, of course, lose mutual information. We had to be careful as to do this in merging in such a way that even though I process the outputs, so I reduce the mutual information, I don't reduce it by much. Okay? So we have to see if we can do this within reason. Okay? So we shall see this. But suppose I do this one, and suppose I now replace this W plus with the channel, let's say, V1. Okay? So now, then this will immediately change these ones to V1 plus V1 minus, okay, and this will become V1 plus plus, this will become V1 plus minus, and so forth. Okay, so you essentially the computations then now become like that. Okay. Now, what is the effect on the average mutual information? Remember, what you're computing was these this mu0, mu1, mu2. What is the effect of this change when I do that? Okay. It has decreased. Okay. But let's see by how much. Okay. Suppose delta 1 was the difference between the mutual information of this W plus and this channel V1 I replaced W plus with. Okay. So here the average has decreased by this. Suppose this number was delta 1. Okay, good. So here nothing has changed. Here the change at this level is exactly delta 1 over 2, right? Because I haven't touched this one. I have reduced this number by delta 1, but I'm summing these two things up and then dividing by 2. This division by 2 is making this change to be delta 1 over 2. Okay? All right. Now, what about this column here? Okay. Okay. In this column, their average is changed by, well, these numbers haven't changed. Okay. These two numbers have changed. Okay. But their sum, remember, is exactly equal to the twice I of V1. Okay. So if you take a look at the I of V1 plus I of V1 minus, it is equal to twice I of V1. Okay. So this number is smaller than the I of W plus, okay, which were replaced by twice delta 1. Okay. So the sum of these mutual informations here is less than what they should have summed before by twice delta 1. But then I'm dividing this 2 by 4. Okay? So the difference I've created, the change here, is also delta 1 over 2, the change in this mu that we are computing. Okay? You can iterate this and then to show that the change in every column here is exactly delta 1 over 2. Okay? So these changes, the change on each so change in the mu is delta 1 over 2. Okay. All right. So okay. So now I can keep doing this. Okay. Suppose that the W minus is also a channel whose output alphabet is too big for my taste. Okay. I don't want to deal with channels whose output alphabet is big. I reduce that one too, and I replace W minus by some channel, let's say V2. Okay. So I do this. I replace it by V2. Okay. And let's say delta 2 is I of W minus I of V2. I degrade W minus in the same way. Okay? So changes now become delta 1 plus delta 2 over 2 in this column, because I get a delta 1 change here, delta 2 change there. The average change is delta 1 plus delta 2. Same argument will say that if I now do this one by the V2 plus, V2 minus, etc. Okay. The changes are going to be delta 1 plus delta 2 divided by 2. The same change propagates to all the remaining levels also. Okay. Now you say, but now perhaps this V1 is now a channel with small alpha alphabet, okay, but maybe the V1 plus is something I don't like to have. Okay. Okay. So you might say I'm going to replace this V1 plus. It has too big an alpha alphabet. I'm going to replace it by a channel with smaller alpha alphabet, degrading it. So let's say I use V1, V2, let's say to V3. Okay. And replace the descendants, of course, by V3 plus and V3 minus. Okay. And suppose that the that this difference but I replaced the V1 plus by, I made a change, okay, all right. So this will now, these are not changed, but I care only about the bottom ones, the downward ones. So this is changing one of these 4 channels in here by this quantity delta 3. So I get here changes delta 3 divided by 4. But now I can do the same thing by changing this one by, let's say, V4, changing this one by V5, change this one by V6. If I do that, I'll get here 4 of these deltas, delta 3, delta 4, delta 5, delta 6, divided by 4. Okay. And this change, this total change propagates exactly to the next column here. Okay. So the things which are here, this becomes also delta 3, delta 4, delta 5, delta 6 divided by 4. Okay. All right. Now, suppose I can ensure that all these small changes I make, all these, well, we don't know if small or not, all these changes I make, all these deltas that are here, suppose each of these deltas are upper bounded by some fixed quantity, little delta here. Okay. If I do that, what I say is the following thing. The change in each column, the change in the first column is delta. Okay. The change in the second column is at most 2 delta. You have a little delta plus little divided by 2, 4 little divided by 4. Okay. So the change, so this change is less than delta. This whole thing is less than 2 delta. This whole thing is, at this point, less than 2 delta. But I'm, of course, going to change all these synthetic channels here by new ones. Okay? I'm going to replace this anytime I see a plus or minus, I'm going to take these channels and change them to something else. So this I'll change by, how much do I use? 6, 7. V6, V7, up to like this. Okay? So this is going less than, divided by 8. There are 8 of these deltas on the top, divided by 8. So it will become less than 3 delta, and so forth. Okay, all right. So at level n, which I'm trying to go into identify the good and the bad channels, the total change I've accumulated is going to be n delta in total. Okay, so if we find the procedure to replace channels with their degraded versions, with the property that the mutual information is changed by less than some small quantity delta. Okay. And if this procedure has the property also that the output alphabet of the new channel is not too big. Okay. But let me not write this thing down because it'll become clear as to what we will have changed by delta. Then after let's say I polarization and degradation steps. So now I see I changed my procedure as to how we compute this tree of channels. I start with a channel, I polarize it to ding and dink. I then degrade each of these synthetic channels that I have. I polarize those, I degrade, I polarize, degrade, polarize, degrade, polarize, degrade. So the procedure is not just vanilla polarization in this tree. Each time I polarize, I degrade to keep the output alphabet size reasonable. Okay? So hopefully, among these properties, I'm also going to add do this thing. Don't change the mutual information by much. At the same time, make sure that you reduce the output alphabet to something manageable too. Okay? So we shall see how to do this. After polarization steps, the average mutual information of the synthetic channels are changed by at most I times delta. Okay? So after I steps at the ith column that you're trying to decide which channels are good, which channels are bad, you only change the mutual informations by I times delta. Okay, suppose I've taken my delta to be, suppose I know what block length I'm designing the channel for. Suppose I'm going to say that I want a block length, let's say 2 to the 20 polar code, a million length polar code. Okay. So the I is equal to exactly 20, okay, because 20 steps are going to do this. And suppose I pick my delta, suppose it is, I don't know, 1 over I squared. Okay. Right? Or if you want 1 over I cubed, it doesn't really matter what you do this. Okay. So then what you have is that this number is small. Okay. So let me actually give an example. Suppose at the end of the day, you find I times delta is equal to, let's say, 10 to the minus 6. Okay, we have chosen your delta to be small enough that it is delta is equal to 1 over million times I. Okay, suppose you had done that. Okay. So now, what is it saying? I have all these channels at the output. The average change is at most 10 to the minus 6. Okay. Let me ask the following thing. What can we say about the fraction of channels at this ith level? Okay, there are these 2 to the I channels in there. How many, or what fraction of them, okay, that have suffered a change which is more than, let's say, 10 to the minus 3. Okay. So the average change is 10 to the minus 6. Okay. I'm asking you about how many have changed by more than 10 to the minus 3. Okay. So think of the following. We have people in this room. Suppose their average height is, let's say, stupid example. Sorry, let's not say average height, because average height can have 10 to the minus 6 is a strange average height. Okay, forget about the heights. Let me just give an example here. Okay. So we have changes. Okay. Suppose you have the jth channel. You have over j. You have 2 to the I channels. So there's j going from 1 of 2 to the I. Okay. These are the changes you have made in these channels. Okay. This average change, I'm saying, is less than 10 to the minus 6. Okay. All right. Now, if within this one there is a fraction of indices of more than 10 to the minus 3 whose change was more than 10 to the minus 3, this could not be correct. Okay. So this sum is lower bounded by the following thing. Summation over, sorry, the sum is it's true, okay, so all right. So I put here summation over j from 1 to 2 to the I. I'm going to put here 10 to the minus 3 indicator function of change j is more than 10 to the minus 3. Okay. So you see, this is a lower bound to this. Okay. If change of j is less than 10 to the minus 3, I lower bound this change by 0. If change is more than 10 to the minus 3, I lower bound by 10 to the minus 3. Okay. So this is what we have done. Okay. So this summation here is equal to 10 to the minus 3 times, here I'm counting the number of channels whose change is more than 10 to the minus 3 and dividing by total number of channels. This is exactly the fraction of channels with change more than 10 to the minus 3. Okay. So divide everything by 10 to the minus 3. So you conclude that this, so this fraction, conclusion, this must be less than 10 to the minus 3. Okay. Maybe I should have asked the question as saying, so that we have more numbers here. Suppose this was 10 to the minus 2. Okay. Then I would have made the same thing here. 10 to the minus 2, 10 to the minus 2. And then we'll end up with the answer being less than 10 to the minus 4. Okay. In probability theory, this would be called the Markov inequality. Okay. To say that a positive random variable cannot exceed its mean by more than a factor alpha with a probability more than 1 over alpha. Okay. You cannot, here's your mean, you cannot exceed your mean by 10 to the 4, factor 10 to the 4, with a probability which is more than 10 to the 4. Okay? So this is the fractions are probabilities, values are the values. Okay. All right. Okay, good. So the fraction of channels is less than 10 to the minus 4. So what now you see is the following thing. I have done the we have done the following. Only a very small fraction of the good channels I have misidentified as being bad. Okay, so the channels which have had mutual information very close to 1. Okay, some of them will now appear as being less than 0.99. Okay, because I have the changes is more than 0.99. So, but the number of these channels that have become worse than 0.99, so which you might think as being now we're going to label them to be bad, those are at most 10 to the minus 4. Okay? So consequently, you're not misidentifying too many of these channels as being bad. Okay? So in particular, for example, choose now delta to be, let's say, this is a random choice. Okay, we could have chosen something else. Choose delta to be 1 over I squared. Okay, then this was going to be now 1 over I. Okay, and let's say the fraction of channels which suffer a loss, which is more than 1 over square root of I, is less than 1 over square root of I. Okay, so not too many channels. This product cannot exceed 1 over I because that's the amount of average change we have made. Okay, so first of all, then for a very small fraction of channels, is the change more than a very small number? Okay, if I is big, so almost no channels, almost zero fraction of channels suffer a loss bigger than almost nothing. Okay, take I to be big. Okay, then so what we have done is that we have identified all the good channels and never misidentify any of the bad channels as being good. Okay? All right. Now the problem is, at this moment we don't know if this procedure is feasible, and secondly, if I can do this and still keep the output alphabet size to be something something small. Okay. Okay. Looks like we are just at the 1 hour mark. Let me stop here, and then when we come back, we will see how to ensure that we can degrade the channels to ensure that both the loss is small, at the same time the output alphabet of the degraded channel is not too huge. Okay? That's what we will do.